Hello community! Today is gonna be amazing! We are looking at reinforcement learning agents here. We have a little tutorial we are based on this video, and we are looking here at Google DeepMind's latest reinforcement learning from human feedback methodology, and it is called here a Jeffrey divergent best of n distillation methodology. And you might say, hey, that sounds amazing. Yes, absolutely. And for my little green grasshoppers, you might say, hey, what is a Jeffrey divergent? It is easy. You have a Kullback-Leibler divergent. You know that this is an asymmetric because you have the forward KL, the mode covering, and the backward KL, the mode seeking mode. And what you do with a Jeffrey divergent is just combine those two, and you average here the forward and backward, and you get a new symmetry. And this is all there is to it. Well, of course, you have to do a new anchor policy that serves here as a reference or as a baseline from which the training policy can diverge here, but only to a control extent. And of course, you have here a moving anchor. And if you look here at the detailed pseudocode of the Jeffrey bond algorithm here, the latest of reinforcement learning by human feedback, you have your forward Kullback-Leibler, your backward, you have your Kullback-Leibler regularization, and then you have the Jeffrey update with the regularization, and you have the update of the moving anchors with an exponential moving average. And this is it. And you might say, hey, that's simple. Is there anything else we can learn? And yes, because if you think about where we started in 2020 by OpenAI, here with learning to summarize from human feedback, where we had here our human feedback, then we had to train here the reward model and to train the policy with our good old friend, the PPO. This is in 2020, and now 4 years later, look where we are. We have J-bond and we have a Monte Carlo quantile estimation. We have here a combination between a forward and backward Kullback-Leibler divergent, and we have an iterative procedure with an exponential moving average anchor. Isn't that fascinating? But you know what? We want to go one step further. And for my little grasshoppers, you might need here a mini introduction. So, you know that we have, if we train our LLMs or vision language model, we have normally 3 training stages. At first, you have the pre-training. Then you have the fine-tuning, normally with a supervised fine-tuning methodology, as you can see the complete code on Hugging Face. And then you have the reinforcement learning from human feedback, where you further increase here the quality of the AI system answers. And you know how it is done? Learning a reward model on the human preferences and then optimizing the LLM to maximize the predicted reward using here a lot of different reinforcement learning algorithms. This is it. If we now want to fine-tune our LLMs more with reinforcement learning, this can be quite challenging because, forgetting happens and the system can forget the pre-trained knowledge of the first step, and there are also some loopholes here in the reward model that can cause reward hacking. Now, there's an easy solution. Policy gradients methodology with Kullback-Leibler regularization towards the supervised fine-tuning policy, and you seek here Pareto optimal policies with a high reward at a low Kullback-Leibler to preserve the general capabilities of the original models. If you're not sure about the Pareto optimal policy, I explain them here in this video about agentic systems. Or we take the alternative as just shown by Google, and we go here with a simple inference time approach of best of n sampling. It can be that easy. But now, if we want to go further, we really have to understand the standard reinforcement learning by human feedback. So, you remember from my videos? The primary objective is to optimize. It's just to optimize a linear combination of 2 elements, the expected reward and the Kullback-Leibler divergence between a current policy and a reference policy. And this is the all defining formulas. And you have all the beautiful elements with the expected rewards and the Kullback-Leibler divergence and the regularization strength that you can choose from. But remember, P here, or pi from English viewer, on reinforcement learning presents here the policy determined by the reinforcement learning algorithm. So what we have a pre-trained and a supervised fine-tuned reference policy. We seek to further align to the new human preferences here in the phase number 3. And to do this, we assume that we have access to a reward model which is trained to reflect the human preferences. Good old OpenAI. But of course we have to do a regularization step, because this helps here to reduce the memory loss or the forgetting and to prevent some reward hacking. So we have the regularization step. Beautiful. So we're inside, yeah, what's the problem? We have our traditional fine-tuning, and we have here, if you want, a continued training after the pre-training phase. The model is trained further on a new data set that is more specific to your particular task at hand. You update now the model using methods like stochastic gradient descent, where the gradients are calculated from a loss function that measures here the difference between the predicted output and the actual output. And you know this is our supervised fine-tuning that you see on Hugging Face and is completely coded. And now there's something new. Fine-tuning now, the second phase, with reinforcement learning. And you say, hey, wait a minute, no, this is phase 2 and this is phase 3. Well, this is the new idea. We want to have a better fine-tuning. And this better fine-tuning we can achieve if we do the fine-tuning with reinforcement learning. Sounds crazy? It is crazy. So, fine-tuning with reinforcement learning introduces now a different approach, focusing on optimizing the models based on a reward system rather than a fixed loss function from our pre-training phase. And this is important for a task where we define an explicit error function. And this error function, you can't find this for every particular task that you think of. So therefore, what is a more general solution? What is more practical? Simply to evaluate the outcomes based on a reward metric. Let's have a look at this. So, reward function, decision-making, policy optimization, and you have the interaction from the environment where you can learn. Step 1, instead of using the standard loss function from the pre-training phase, reinforcement learning utilizes now the reward function that provides feedback on the quality of the outputs based on specific criteria you defined. And this reward guide now the learning process. Reinforcement learning views here the fine-tuning process as a sequence of decisions where each step, so this means each single modification to the model during the generation, is now considered a decision that affects the further outcomes. And as you know, in reinforcement learning, the goal is to develop a policy that maximizes the cumulative reward for the system. And this policy dictates the adjustment to the model parameters, effectively learning here the updates in our fine-tuning phase. And reinforcement learning based fine-tuning, the model interacts now with an environment, which could be historic data, which could be an online computer simulation. And those environment data, they provide now a feedback in the form of rewards. And this interaction is now critical as it shapes here the learning process and the adaptation of the model. Sounds theoretical? Never mind, I give you an example. So what we are up now is a complete new methodology. Something that breaks with our classical expectation of pre-training, fine-tuning, and reinforcement learning by human feedback. Why? Because we have a very specific downstream reward function, because we are not operating anymore here in language, but we are operating now in a real application, in bioinformatics, in genetics, in, drug development. We now employ now our AI system, and those AI systems should provide some value to accelerate here drug discovery, new medication. Imagine you have a generative AI model and can create new chemical structures. And this AI system might produce a wide variety of molecules, some of which may not have desirable drug-like properties. But by incorporating now a scoring system into the training process of this AI, we can now guide the model to focus on generating new molecular compounds that are not only structurally valued and stable, but also have a high likelihood of being real effective drugs. Wouldn't that be great? So, optimizing for a high QED, and no, this is not the quantum electric dynamics, but I will show you in a second what it is. we can guide the model to come up with suitable candidate molecular compounds, molecular clusters for drug development, streamline and accelerate drug discovery. This is what we're looking for. AI with, in the fine-tuning phase, we employ reinforcement learning for a real complex reward function. So what is QED? It stands for Quantitative Estimate of a Drug Likeness. And this means the fine-tuning of a model to generate a molecular structure, a very specific 3D molecular structure. And this has properties making those molecules more likely to be useful as drugs. And bioinformatics has defined here all the important molecular properties like molecular weight, hydrophobicity, the number of hydrogen bonds in the donors or acceptors, the number of aromatic rings, the number of rotable bonds, and you got the idea. And now to the most important piece of information. By optimizing now our generative AI model to produce now these particular molecules with a high QED score, the model is now biased towards proposing here in the generation of novel molecular structures that have now a high chance of possessing these drug-like properties that we are looking for. So this means in the chemical space that we are exploring for new candidates, we have now a much more targeted exploration in the chemical space. We have a path forward. So this means optimizing here our models for a high QED means simply fine-tuning a model to generate novel molecular compounds biased toward those that have a favorable properties for drug discovery, like our QED drug likeness metric. So if you take a step back, you see, hey, this is just an optimization process we know from physics. So we optimize now a diffusion model for a high QED score, and we use techniques like reinforcement learning, where the model is now fine-tuned after the pre-training phase by rewarding the model for generating molecules with a high QED score. This is it. This simple sentence defines the new ideas going forward. And my eagle-eyed viewers now that I have not told you particular, but look at this. We use here a diffusion model. We do not use a classical transformer like your Gemini or your Sonnet. We are operating here with a diffusion model for a reason. So therefore, we are now working with diffusion models, with entropy regularized diffusion models for a high QED, like reinforcement learning, where we fine-tune the model by rewarding it in a specific way. Sounds complex, is complex. Great. So let's come back. Short summary. We have a problem. We have our pre-trained diffusion models. They are able to capture general data distribution. Think about a movie, a video, or a simple image. This is a real general data distribution in a two-dimensional sphere. However, we often need them to generate samples optimized for a specific downstream task like QED. Not just, hey, reproduce the same image, but, hey, I have a different task like I want to find a new molecular compound. So I give you here a specific downstream task, QED, measured by a reward function. And now you see what's happening. Those diffusion models can be seen mathematically as a sequential decision-making process. So this means that each denoising step in the diffusion model is a decision. And reinforcement learning is naturally suited here to solve this, allowing us to optimize here our AI model to maximize here the reward in this particular reward configuration. So we are talking now about reinforcement learning fine-tuning. So you see, we break with the tradition of our three-phase model, pre-training, fine-tuning, and RL. And now we have reinforcement learning fine-tuning on diffusion models. And this is interesting. And it goes beyond our standard fine-tuning that you know from text or vision. Because the traditional fine-tuning models often rely on modifying the loss function that was used during the pre-training of our models, of our gammas, of our llamas, of our whatever. But now, with this new methodology, the reinforcement learning offers a more flexible approach by directly optimizing for the desired reward. And this reward can be complex. So again, fine-tuning via reinforcement learning. Brand new, makes you head scratch, but yeah, this is now a new thing. Reinforcement learning is suitable for fine-tuning diffusion models because the process of denoising in our diffusion model can be framed as a sequential decision-making problem in mathematics. So, isn't that beautiful? So remember, diffusion models we choose over our classical transformer models because they are more able to capture complex data distribution. And there's a need to tailor them even further when the desired output is a specific performance metric rather than just a reproduction of a data characteristic. So we just do not say, hey, reproduce here the image, but we tell now, hey, I have a specific performance metric that I would like you as a diffusion model to optimize. And we're working here in biology where the output, like a three-dimensional DNA sequence, needs here to satisfy specific functional criteria. And think about why is a classical transformer not able to do this? I will give you the solution in a minute. So therefore, again, reinforcement learning for fine-tuning. Reinforcement learning emerges as a suitable method for this kind of fine-tuning due to the sequential decision-making nature of the diffusion models. Each step in the diffusion process can be viewed as a decision point where the model chooses to modify the sample based on the reward function. Now, if you think about this video from MIT where I showed you how you can use multi-AI agents in an agentic system to develop new material science like new alloys for space shuttle. Now, you might say, hey, why did we use transformer-based AI systems, multi-AI systems, multi-agent system here in this with MIT, and why suddenly we're using diffusion models here? Now, think about in alloys, in crystalline structures, we have a beautiful translation symmetry. So we do not need to be as critical to complete new spaces, high complex spaces. But because we have this beautiful crystalline structure, we can work with transformer. But the moment we go in biological system with three-dimensional complex molecular structures, DNA sequences, we need better performance models, and those are diffusion models. Great. So, short summary, reinforcement learning-based fine-tuning. Goal is to optimize the distribution to maximize the expected reward, formulating the fine-tuning as an RL problem where each step in the diffusion process is seen as a decision point. Yes, I know this was number 3, but this is so important because if you compare it to non-reinforcement learning approaches, this reinforcement learning is particularly useful. Why? Because if we generate with our AI model now high reward samples, we can do this even if those new generated high reward samples, they can lie outside of the training data distribution in the fine-tuning phase. So if you want to discover real new molecular compounds, you can do this with reinforcement learning. In other non-reinforcement learning approaches like rejection sampling or conditional diffusion model, they will fail because they can't generate here those samples that lie outside of the training data distribution. Much more complex in detail, but just to give you the idea. But of course, you can choose another reward function. You do not have to go with QED. What about cell specificity for DNA sequences? The rewards can either be known or learned from the feedback data, the interaction that comes back from interacting with the environment. You have a lot of possibilities with these methodologies. So again, based on the current state, and this is now for us a current molecular or protein structure in bioinformatics, the reinforcement learning agent selects now a particular actions. For example, it adds now a chemical molecular component to our protein structure. It then observes the outcome, how the addition of this changes here the three-dimensional structures or the stability properties of those new molecular cluster, and receives a reward. Hey, this was good, or no, this is completely unstable, based on the desired properties like stability and so on. So you see, the idea is simple. You just have to code it and let the AI run. Really? Is it that simple? Not really, because we have a lot of different reinforcement learning based fine-tuning algorithms that are either non-distribution constraint or that are distribution constraint. So what does it mean? The non-distribution constraint like PPO, they are particularly beautiful since those methodologies allows the model to deviate from the training data distribution, enabling here the exploration of new areas in the output space, in the chemical possibility space of molecular compounds. However, sometimes you do not want this. You want a distribution constraint approach, like if you want to have an AI modeling system. If you have data from financial transaction and you want to know, given my historic knowledge of financial transaction for whatever it is, how can I make sure that whatever the AI model predicts now, that it is similar, that it is not going crazy, but it is real close to the known distribution of my historical financial metrics. So in this way, I can prevent the system of coming up with complete new misleading conclusion. I want that all the new AI predictions are real close to the financial known metrics. Then you go for distribution constraint approaches like ABC. You see, a little bit complex. I'm talking about complexity. This is something for the evening. Think about, why do we use not the transformers, the classical transformers like a Gemini model or a Sonnet model? Why do we go with diffusion models? You really have to get this. You have to be absolutely sure that in applications like protein folding or drug design, the ability to control here the generation process of new ideas at each step on the way, this is crucial for ensuring the viability and the functionality of the end product. You have the optimization step going forward step by step, and the system has to adapt continuously. However, think about our classical transformer. We have a sequence-to-sequence task. You want to reproduce here a summarization of a PDF document. You go with sequence-to-sequence task. This is great for this particular task, but if you want to not have to go from a complete sequence to a complete sequence because you want to discover new opportunities on each step that you take, you have to go with diffusion models. So the choice that you have between diffusion model and the transformers depends largely on the specific requirements of your task at hand. It includes the nature of your data, the required stability and control in this generation process, and the complexity of the data distribution that are to be modeled. For tasks involving a gradual, iterative generation or the manipulation of real complex, continuous data, the diffusion models often provide significant advantages over our classical transformer models. Great. Now this was the introduction, ladies and gentlemen. Now we can start with the video. Yippee! Yes. So here we go. Diffusion models. What are they really? They are really denoising diffusion probabilistic models, DTPMs, and they have a forward and a reverse process, and we will look at this. Plus, I told you we have a score-based diffusion model. So we have a continuous time formulation of the diffusion model. You have the forward and the time reversal stochastic differential equation that we have to solve, plus the score function estimation and the equivalence to our DTPMs, plus the complete new topic of fine-tuning with reinforcement learning. And you might say, that sounds amazing. Yes, I know, because we have, in addition to theoretical foundations here, so we go for entropy regularized Markov decision processes, and we'll have new key concepts like soft Q function and soft Bellman equations. And the fine-tuning happens, of course, in the entropy regularized MTPs, where we frame the fine-tuning process within the context of this entropy regularized Markov decision process. And then on this, we build here our reinforcement learning based fine-tuning. Great. So let's start here, and you might say, hey, finally some formulas. Yes, we are here entropy regularized Markov decision processes. They are so important for our reinforcement learning due to the ability to encourage your exploration, and they ensure a more robust and stable policy learning. Great. So what it is. Now, you know what is a Markov decision process. It is defined as the following. Beautiful. And the standard goal here in reinforcement learning is to solve this equation. You have the argmax where E is here the expectation induced both policy P or pi and the transition dynamics as follows. Beautiful. In an entropy regularized Markov decision process, we consider the following regularized objective instead. So we have an additional entropy term to our reward function, promoting policies that maintain a higher level of uncertainty in the action selection. And this is important because in a complex environment, the agent might get easily trapped in a local optima or fail to explore here, to discover here optimal policies. So we have here this additional term, and now suddenly we have to solve this. And this is here where we will use here a soft optimal policy approach. Beautiful. So this is the basis where we start off. And then, of course, the crucial question is, how do we solve this equation? You know, this number 12 here. This is where we need to solve this, and our solution to those equations are exactly what we are looking for, because this is our fine-tuning algorithm of the diffusion models. And to see these algorithms, we rely here on the critical concepts of entropy regularized MTP, and our soft optimal policies can be expressed analytically as a blend of the soft Q function and the reference policies. And those soft Q functions in their term are defined as solution to the equation known as the soft Bellman equations. And now it starts. So, soft optimal policy expressed as a blend of soft Q function and reference policies, and we define the soft Q function as the following, and I will give you here the literature. This is from Genentech, Princeton University, and UC Berkeley, and those authors are great, and I give you here the literature. You have to have a look at their scientific publication, and they define here the soft Q function, and they can solve this. And now we have a transformation into a soft optimal policy that can be described as this, and we can solve this mathematical expression. And this is now our code base. This is what we will code now. Now, the complexity of our methods in reinforcement learning, you know, and maybe for my little grasshoppers, a very short introduction, we have more or less three categories. You have the Q learning, straightforward, powerful, discrete action space, but struggles, of course, on continuous domains. Or B, we have the policy gradient methods that shine in environments with continuous action spaces and can learn stochastic policies, but suffer from a high variance in our estimates. And the best of both worlds, the actor-critic models. They aim to reduce the variance of the policy gradients method while retaining the ability to operate in continuous domains. They improve the learning stability by separating the policy guidance by the actor model from the value estimation by the critic model. So, best of both actor-critics models. If you want to learn more about 1, 2, 3, here's number 1, value-based algorithms, value function optimization goal, policy derivation, the pro and the con of this methodology. If you really want to have a deep dive here in the Q function, in this video, I go from A star to the Q function to Q star, multi-step AI reasoning. This is the video for you. We can apply this Q learning, for example, in protein synthesis. Those are 3 steps: sequential decision making, reward function design, and the policy update and the refinement. Number 2, policy-based algorithms like our policy gradient. How it works: you have a policy representation, pi, you have an optimization goal, a gradient computation, the pro and the cons of this methodology. And as I showed you, the best of both worlds. We have the advanced actor critique, the A2C or the PPO, where you combine the strength of both the actor, policy, critic, value function, pro and cons of those systems. But remember here, the action space can be discrete. Now you know that there are a lot of other methodologies like DDPG, SAC and TD3, all advanced reinforcement learning algorithms primarily used for continuous action space problems, because this is exactly where we are with our 3-dimensional molecular clusters. If you want to learn more about the deep deterministic policy gradient methodology, or about the soft actor critique model, or about the twin delayed deep deterministic policy gradient methodology, here it is for you. When to use what model? All 3 algorithms are suitable for environment with continuous action, but I like SSE and TD3 more for their stability. So I would prefer SSE and especially TD3 over DDPG. And now to the most important point. We have now a new publication by Genentech, Princeton University and UC Berkeley about a new tutorial. And now, with this video, you will see that this tutorial becomes easy. You will understand it immediately. And it is about understanding reinforcement learning-based fine-tuning of diffusion models. A beautiful tutorial, Genentech, UC Berkeley, Princeton University. Have a look at this, July 18, 2024, just 4 days ago. Amazing, look at this. They give you here a complete tutorial, diffusion models, fine-tuning, entropy, regularized MTPs, theory of reinforcement learning based fine-tuning algorithms, distribution constraint approaches, we talked about this. Then they have known differential reward function, black box reward feedback, and unknown reward functions. Those are beautiful functions where the environmental feedback defines this reward function. Have a look at this. Or if you want to have a look at even more advanced flow-based diffusion models or unnormalized distribution, you can go with Markov chain Monte Carlo simulations. And maybe if you're green grasshoppers, you need my video to enable you to understand here the entry point. Because you see they start here with soft Q function, soft Bellman equation, which is great. But if you start with this and you do not understand here the main ideas in the development that is going on now for 4 years here, then maybe you are a little bit lost. And this is why I did this video, to help you that you are able to read here the latest tutorial on the latest methodology on reinforcement learning by human feedback. And now those concepts and those formula, they will become our new code base. Because we have now to train a model, but at first we have to build here the training functionalities to code a model. And exactly those equations are now what we will code. And of course, we have a GitHub repo, reinforcement learning, fine-tuning, diffusion here for biological sequences. Go there, have a look at this. You see, just 3 days ago, there was an update. If you want to get a hands-on experience, but you have to have a little bit of knowledge of bioinformatics and maybe of proteomics or pharmacogenetics or whatever you like. So you see, this is the physics. This is the mathematics that we need for our AI system, and this is what we code in our AI system. And therefore, I try to explain those ideas here to my audience, because if you just look at the code, you might be disappointed. You might not get the idea behind the code, because the code is already an optimized version of those mathematical formulas. So therefore, I would recommend you do not start with the code base, but you start with trying to understand what the hell is going on with soft Q-Bellman function and equations. So therefore, this is the documentation. If you are in any way in reinforcement learning based fine-tuning of diffusion models, in any way in bioinformatics, you have to see this publication by those researchers, Genentech, Princeton University, UC Berkeley. Great. This is the end of the video, but for my little grasshoppers who say, okay, if I'm now interested to enter this area of modeling biological processes, and if I want to build AI system for biological processes and not for simple text things like we use currently with Sonnet or simple code, but if I want to enter complex biological processes with AI, what is my guide? Well, here it is. If you do something like protein folding or molecular synthesis, where each addition of a nucleotide or a molecular complex can significantly affect the final three-dimensional structure and the function and the symmetries and the chemical abilities of your cluster, reinforcement learning now operates effectively by using here a well-defined reward system and learning through trial and error. It really learns by the feedback from the environment. Is this a potential three-dimensional structure with this added chemical compound molecules, yes or not? So therefore, how we do this? We have to set up the environment and the action. Beautiful. Environment would be a simulation or a model where molecular or protein sequences can be manipulated. Each action in this environment represents a possible modification to the molecule cluster, or the protein sequence, such as adding a nucleotide in a DNA sequence or a residue in a protein chain. Whatever you have, you can do it. Then you have to define your reward function, because this is crucial in guiding here your reinforcement learning agent in the fine-tuning phase, and this must be really carefully designed to reflect the objective of the biological modeling, because you get an immediate feedback. And if a protein stability can be quickly computed from its current sequence configuration, from the new molecular compound added here to the three-dimensional molecular structure, the reward could be directly linked to the stability measurements. So if you have a computer simulation that goes in real time, you get exactly here the feedback from the environment, and you can say, this is a stable configuration, yes or no. However, if you work with complex biological molecules, it is sometimes important to have some delayed rewards. Because imagine you have a particular 3D molecular cluster, and then you just add one new component, molecular component. It will not fold in a particular way that you want, but maybe you have to add 3 additional components, and then suddenly the complete three-dimensional structure will make snap. And it will change its 3D structure in exactly the way, or exactly will fold in the way that you want it. So sometimes a delayed reward, adding 1, 2, 3 elements, is helpful, because the combined effect of these 3 added elements may be exactly what you were looking for. Great. Step number 3, learning through interaction. The reinforcement learning agent explores now various actions. This means modification to the molecule or to the DNA sequence randomly or semi-randomly to gather data on the effects. And now over time, trial and error, the system now starts to understand which action, which molecules lead to better rewards, lead to more stable configuration. So it begins to exploit this knowledge to make more informed decisions for its next steps. Policy. Sequential decision making, each step is adding to the sequence, is now a decision point, and based on the current state of our model, for example, the current three-dimensional molecular structure or a protein structure, the agent, the reinforcement learning agent, now selects an action to add a molecule, observes the outcome, how the addition now of this molecule changes the overall three-dimensional structure, changes the folding, or changes some electrochemical properties, and receives a reward. This might be positive or negative based on desired properties like stability or QED or efficacy or whatever you have defined. Isn't that beautiful? So next step, easy, update the policy based on the rewards. You want to have a self-learning system. So using, in the simplest case, algorithms such as Q-learning or policy gradients, the RL agent updates its policy, which dictates the probability of choosing each action based on the state that the system is in. So the policy evolves to maximize the cumulative rewards, which are aligned with the scientific goals of the project. So the policy update mechanism is simple. The RL agent adjusts its policy, its strategy, how to proceed, to increase the likelihood of choosing actions that have historically led to high rewards. Give you an example of the reward design in protein folding might be negative for configuration that are physically impossible or unstable in our computer simulation, and it might be positive the reward for maintaining the correct angle and the correct distances in our molecular cluster that are known to be a stable configuration. Or in drug design, the rewards could be assigned based on the QED, on the drug likeness of a molecule, or its synthetic accessibility, or a predicted efficacy against a target protein. You see, your combination and your reward structures really depend on your particular task. But isn't this a beautiful system? And I know in the beginning of this video, we break with our classical three-step approach of pre-training, fine-tuning, and reinforcement learning by human feedback. And switching here to the diffusion model, we see that we have now a reinforcement learning based fine-tuning phase that is able to do so much more, to make our AI predictions so much more performant, that it is amazing. And I wanted to show you this, and I want to give you this literature, and I want to give you this tutorial by Genentech and Princeton University and UC Berkeley, because if you look at those pages, those are amazing information if you want to enter here this area of AI bioinformatics. I hope you enjoyed this video. I hope there was something new for you that you really thought, hey, maybe I could use this in my AI models, and it would be great to see you in my next video.